everyone, I'm Anya, master student from the Moscow State University, and I'm going to present you our results of phase equilibrium modeling for crustal xenoliths from the Udachnaya kimberlite pipe in Siberia. So, Udachnaya kimberlite pipe is disposed within Siberian craton in Dolbin terrain, and these xenoliths were the focus of previous studies. So we know these rocks are garnet, granulites, amphibolites, plagioclase, and endobites. So first of all, the main result of previous studies is the timing of two major events, such as crust formation during Neocean and metamorphic event during Paleoproterozoic, associated with the amalgamation of the craton. And the next result is the estimating of wide range of pressure and temperature metamorphic conditions. I should say that the phase equilibrium modeling were never before applied for these xenoliths. Our rocks are garnet granulites composed of clinopyroxene, garnet, plagioclase, and ilmenite as an accessory phase. And also orthopyroxene is major for one sample, and amphibole and scapolite are major for other sample, in addition to these four phases. A typical feature or features of our samples, besides their beauty, are granuloblastic texture, the lamella within clinopyroxene cores, the significant amount of mineral inclusions in garnet grains, such as clinopyroxene, amphibole, ilmenite, apatite, and sulfide inclusion, and also lamella of magnetite within ilmenite grains. Kimberlite-related alteration are recorded by intergranular villets composed by phlegopite, carbonates, and serpentine. As I showed you on the previous slide, clinopyroxene are zoned and contain chemically homogeneous cores with lamellas is made by low calcium pyroxene and ilmenite. Rims are narrow and they show zoning with increasing of magnesia number and decreasing of alumina content. And also, rims are lamella-free. Interesting thing is that clinopyroxene contain a high amount of aegirine molecule, and jadeite content is up to 3 molar %. As I said, clinopyroxene occurs as a matrix grain and also as inclusions in garnet. And if we will look at these plots, alumina content versus magnesia number, we can see clinopyroxene inclusion composition overlaps only rims of matrix clinopyroxene compositions. And also clinopyroxene inclusions are usually lamella-free. Garnets in our samples is pyroalmandine with 40-19 mole % of grossolar, and also they show lights divalent calcium zonation. Plagioclases are oligoclases or undesigned with small amounts of alkali feldspar, and they show light zonation too. Amphibole is measured only in this sample, and it's pargosite by Lie classification. And orthopyroxene is measured only in another one sample, and it shows zoning with decreasing of alumina content towards the rims. Phase equilibrium modeling were realized using the James Connolly perplex, and we assumed the using of effective composition is more appropriate than using of bulk composition because our xenoliths are alterated by kimberlitic melts. So we used modes of minerals, the densities, and composition of each minerals to quantify the effective composition. Firstly, we tried to calculate phase diagrams using effective composition with whole clinopyroxene grains, but we couldn't reproduce the equilibrium composition of each major minerals. So we decided it was wrong to use whole clinopyroxene grains because mineralogical data hints that clinopyroxene were probably isolated from the metamorphic process. So we excluded clinopyroxene cores from the effective composition. As a result of phase equilibrium modeling, we calculated temperature fugacity and pressure temperature phase diagrams for all samples. The pink field here represents the field with appropriate paragenesis, and the star represents the observed temperature, observed parameters values that were reconstructed using intersection of isoplate of chemical composition of each minerals. Firstly, we calculated temperature fugacity diagrams to observe temperature and fugacity values. And then, using the fugacity values, we calculated the amount of oxygen to add to the effective composition and calculate the pressure temperature phase diagram. And then we observed the corrected pressure and temperature values. As a result, we reconstructed temperature and pressure for all samples. Temperature are 650 degrees, and pressure are 810 kilobars. And also, we reconstructed reduced condition up to 3.3 log units below Funku buffer. I should to say the temperature observed by conventional thermometry, like Clinopyroxene garnet and orthopyroxene garnet thermometry, correlated well with temperature observed by modeling. Also, we used titan oxide thermometry by Anderson and Lindsay, and we observed much higher temperatures and more oxidized conditions. So we think these values represent the starting stages of metamorphic process. These parameters could be interpreted as a recording of Devonian paleogeotherm, but in this case, these values should be corresponded with conductive geotherm is reconstructed by data of mantle xenoliths. But if we will look at this plot, pressure temperature plot, and we will extend this line to lower crustal xenoliths condition, we will see the much colder temperatures under the 400 degree of Celsius. And it is much colder than this temperature we observed in modeling. So we think the real temperature in the lower crust in Devonian was lower than 400 degree of Celsius, that is correspondent with this geotherm. And our temperatures, it is just recording of kinetic related determination of mineral reactions. So it is just system closure temperatures. By all mineralogical and petrographical data, in our sample, garnet evidently occurs along with Clinopyroxene core isolation and Clinopyroxene rims formation. And plagioclase was likely recrystallized and partially reacted out to form garnet. Usually, garnet formation is described by this Newton and Perkins reaction, but quartz is absent in most of our samples, so we described garnet growth by this reaction involving titan oxides. All of this reaction shifts to right while cooling occurs. And this titan oxide contribution is also supported by elevated titan content in garnets. This reaction is really interesting because it implies the consumption of oxygen from the fluid phase if it exists. So this reaction could explain this reduced condition we observed by modeling. We calculated the activity of the components of the fluid using fluid exam module in Perplex. And if we will look at this plot, component activity versus fugacity, this gray area represents the reconstructed values of fugacity. So for the most of the samples, besides this one with amphibole as a major phase, we should look at these solid lines. And these blue lines represent the water activity. And within this gray area, water activity stays relatively low. And for these sample with amphibole as a major phase, we should look at this dotted line. And here, the water activity is pretty high, and it corresponds with the amphibole as a major phase in this sample, and also with the most oxidized condition for this sample. I can say that in all samples, apatite are enriched by fluorine and chlorine. Amphiboles are enriched by chlorine, fluorine, and sulfur trioxide, and also scapolite in the sample. In this sample contains sulfate and carbonate groups. And these features are pretty typical for fluid deficient metamorphism in meta-igneous complexes. So we think if a fluid phase existed during metamorphic reactions in the studied mafic granulites, it was represented by a small amount of polyionic brine, which was able to impose low water activity. And this assumption also explains why these temperatures are low, and they corresponded with amphibolitic phases condition, not granulitic. Our explanation is pretty simple. We think that lack or deficit of the fluid phase during metamorphic reaction just block reaction of amphibolitization. So clinopyroxene and other minerals just can't be transformed into amphibolite. And final interesting detail of our work is the composition of the clinopyroxenes. I say that the clinopyroxene contain high amounts of aegirine molecule. So you can wonder such clinopyroxene composition under reduced condition. But yes, it's interesting, surprising, but it's real, and we confirmed it. So main conclusion here is mafic granulites from xenoliths with studies were formed under amphibolite phases condition. Phase equilibrium modeling reveals reduced oxygen fugacity during metamorphism, up to 3.3 log units below Hinku buffer. We think the metamorphism was fluid deficient, and granulites were equilibrated at temperature much higher than can be reconstructed from conductive geotherm. That's all. Thank you.
Thank you. That was really interesting, and they look like really, really nice rugs, really fresh.
Thank you.
There haven't been any questions that have popped up, and here we go. First one appears. Okay, so Hugo Morea says, have you tried to date any of the phases of these xenoliths? Do you think the main pathogenesis could have been affected by fluids derived from the kimberlite pipe?
Can you please repeat it? Maybe
yeah, sure.
Look into the chat.
The first part is, have you tried to date any of the phases in the xenoliths?
In what?
Have you tried to date any of the minerals in the samples?
No, we used the data of previous studies.
Sure. Okay, so the second part to Hugo's question is, do you think that the main mineral assemblage could have been affected by fluids derived from the kimberlite magma itself?
We think the main influencing here is the forming of these winlets in the intergranular space, but we can't be sure that any composition of minerals are affected by kimberlites. We can't assume this. There is no evidence for this.
Okay. Nick Roberts has a question. If the xenolith was cool in the Devonian, when it became cool, Nick, if the xenolith was cool in the Devonian, when did it become cool in time?
We think cooling occurs during all the time from the Paleoproterozoic to Devonian, when they were transported to the surface. So it was really, really long cooling during the 1.4 billion years.
Okay, great.